Hello, I am Oscar Begley. My roles throughout this project were project lead, experimental lead, and creating the workflow chart.
Hi, my name is Yash. I was in charge of the workflow diagram in this project. I was also in charge of the risk assessment.
Hello, my name is Garani. Throughout the project, I'm in charge of different types of tables and justification for weights and the final editing videos.
Hello, my name is Ihan Godfrey. I was responsible for handling the Gantt chart, assisting with prototyping, and various different background research.
Hello, my name is Don. I am responsible for WDM table, generating and evaluating solution and visualization of the prototype.
So far, in 2025, over 866,000 hectares of forest were burned during forest fires in British Columbia. This releases contaminants into the air, such as sulfur dioxide and nitrogen dioxide, making rain acidic. This decrease in pH will negatively impact soils within our environment. The current solution is adding lime water, calcium carbonate processed from limestone mixed with water into the environment. This process is relatively CO2 intensive and unsustainable. Our goal is to find a solution that works as effectively and is more sustainable.
In order to do a proper analysis of both the problem and a solution, we need to do a stakeholder salience chart. To do this, we organize the stakeholders in aspects of production, transportation, creation, and application of our solution. The primary stakeholders, first of which being rights holders, were First Nations, municipal, provincial, and federal governments, along with environmental bodies.
An important concept we used throughout the design process was cost-benefit analysis. Once we set up what our problem is with a stakeholder analysis, a simplified version of cost-benefit analysis was used throughout the project, setting a baseline of pH and cost specifications and trying to improve sustainability from that baseline. The aspects of sustainability we valued most were reduced emissions, recycling, reuse of materials. Doing constant iterations on our understanding throughout the design process is to best understand how each change affects sustainability.
In order to have our solution be on par with industrial lime water, we set 5 design specifications to achieve our goal. Making sure our solution does not create more problems than it solves, making sure our solution has the same alkalinity as industrial lime water, having our solution be created, transported, and applied both ethically and legally, being able to complete all aspects of our solution within the time frame of this project, and having all resources used throughout the creation of this solution be under a budget of $100.
We began our prototyping by modeling both pH changes with a virtual prototype, using a chemical model for pH change with each of the materials. We moved on to a physical prototype to verify the alkalinity of our alkaline solution, using pH strips and multiple test samples of the different ratios of our alkaline materials. Our final prototype was a comprehensive physical prototype. We used the most sustainable combination of alkalinity to industrial lime water, 2/5 calcium carbonate from lime, 2/5 from marble, 1/5 from wood ash, and used it to balance the pH of the sample soil affected by acid rain. We took 30 grams of sample from Okanagan soil and decreased it to its pH of approximately 5. We then added our lime water solution drop by drop to get its pH to 7.
Our solution to this problem is an alkaline solution made of a composite of alkaline materials, prioritizing local and recycled materials. The 3 materials we used in our project were calcium carbonate from limestone, marble mined in Vernon, and wood ash leftover from forest fires. And as this solution is a comparable pH to lime water, it can be applied the same way as the industrial lime water, right into a neighboring body of water to enter the water cycle of that ecosystem. And the exact values we calculated to complete a pH change on acidic soil pH of approximately 5 back to a healthy pH of approximately 7 was by adding 1 milliliter of our alkaline for 30 grams of acidic soil.
Most of the limitations with our solution come from the lack of time and resources during our prototyping stage. Our prototype had to be created in small batches that made a large-scale application of this solution out of the scope of the project. As well, we were not able to do a long-term assessment of the soil using this solution. Despite these limitations, we were able to create an alkaline liquid of comparable pH with industry-standard lime water, using materials that can be recycled and sourced within the Okanagan area. With more testing and iterations, our current trajectory, we will have an industrial-grade and produced limestone water solution made of sustainable materials from the Okanagan area.